This is Group A2 with Stephen Woodruff, Matt Goldstein, Daniel Moore, and Brandon Gardner doing linear and binary searching algorithms. For more videos about discrete mathematics, visit www.noatom.com. What is an algorithm? A finite sequence of precise instructions for performing a computation or for solving a problem. What are some of the properties of algorithms? Input. An algorithm has input values from a specific set. Output. Each set of input values of an algorithm produces output values from a specified set. The output values are the solution to the problem. Definitiveness. The steps of an algorithm must be defined precisely. Correctness. An algorithm should produce the correct output values for each set of inputs. Finiteness. An algorithm should produce the desired output after a finite number of steps for any input in the set. Effectiveness. It must be possible to perform each step of an algorithm exactly and in a finite amount of time. Generality. Procedure should be applicable for all problems of the desired form, not just a particular set of input values. Our first type of searching is linear search, also known as sequential search. Given a value or element, linear search goes through the list in order and will find that element. It will continue until the element is found, going element by element. If it does not exist, the solution is 0. Here is an example of linear search written in pseudocode. Binary search. Binary search is used when a list has increasing size. It proceeds by comparing the element to be located in the middle of the list. The list is then split into two smaller sublists of the same size, or where one of these lists has one fewer term than the other. The search continues by restricting the search to the appropriate sublist based on a comparison of the element to be located and the middle term. Here, binary search is written in pseudocode. Now we will have some examples. Here is a simple list where we are searching for the number 4. We are going to use linear search to go through this list. With linear search, we would start out with the first element, which is 1. 1 is not the element we are looking for because it is not 4. So, for linear search, we'd move on to the second element and check 2. Once again, 2 does not equal 4. So we would move on to the third element. We would see that 3, once again, does not equal 4. So we would move on to the next element. This time, we are going to check 4. And since 4 is the element we are looking for, we would stop and return the position of that element. Now let's look at binary search for this list. Binary search has a starting and an ending point. So, our starting point for our first search would be 1, and our ending point would be 6. The first element to be checked would be 3, since it is in the middle. We would notice that 3 does not equal to 4. So, we would move on and move our I, because the element we are our starting point would then move to 4, because it is the place we checked plus 1, and our ending point is 6. Now, we would check 5. And since 5 is greater than the element we are looking for, J would move to 5. So once again, our starting point is 4, and our ending point is 5. So we would check 4. And since 4 is not greater than 4, j would move to 4, or our ending point will move to 4. Since our ending point is now at 4, and our starting point is at 4, we must have found our element. We check to see that it is equal to the value we are searching for, and we give out its location. Now, while it seems like binary search may have taken longer, binary search scales much, much better than linear search. We have another example. Here, we have 20 elements. With linear search, we would have to start out looking at the first element. And then we would move to the second element, because it's not equal. And so on and so forth until we finally make it all the way to 15. And this is only with 20 elements. Now imagine a much larger scale. But with binary, we have our starting point at 1 and our ending point at 20. We would then split this into 2 lists, 1 through 10 and 11 through 20. We would check the last element of the first list, which is 10, and notice that 15, the number we are searching for in this case, is greater than 10. This would move our new starting point to 11. So now we break it up into 2 more lists. We have 11 through 15 and 16 through 20. Once again, we check the last element of our first list, which is 15. 15 is not greater than 15. So our ending point is now going to be 15. So now we split the list again. So we have 11 through 13 and 14 through 15. We're going to check the last element of the first list again, which is 13 now. And 13 is less than the element we are looking for. So our new starting point will be 14. So once again, we split the list. We check 14. 14 is not going to be greater than the element we are looking for, so our new starting point will be 15. This is also our ending point. And at this point, it will check to make sure that that element is equal to the number we were searching for, and it will output the position of that element. This took many fewer steps than that of linear search, and this is only with 20 elements. As things scale, binary search will take many fewer steps than that of linear search.